Hi, so now today we're going to be having a look at the parabola. We've been through the circle, the ellipse and the hyperbola, seen there's a lot of similarity between the ellipse and the hyperbola in terms of the forms that we're given. And we've looked at Cartesian and parametric forms for all of these things so far. So it's the parabola today. Parabola is more straightforward to look at than the ellipse and the hyperbola. It's a simpler form to work with. We tend to do the ellipse and the hyperbola together because they're quite similar. But now we've got the parabola, which hopefully should be a little bit more straightforward. Not that you've been having difficulty with the ellipse and the hyperbola. I've seen that work. It's been looking good. So let's crack on and get into it. Remember that our parabola is what we get from slicing through one of the sections of the cone. We get the parabola in that way. We get the circle by going straight across. We get the ellipse by cutting across from both sides and one half of the cone. We get the hyperbola by cutting down, so it goes through both parts of the cone. Just start off with, have a look at the focal properties of a parabola. So if we have a headlight or a spotlight, if we put, say, in a car headlamp, we have the light source, the bulb, at the focus of the parabola. As the light rays come out of the parabola, of the bulb, they hit the parabola and they come back so that they all head off beyond the mirror in parallel lines. So the light all ends up going in the direction that our car is traveling. Okay, that's what we want to be seeing, that the light is all in the right direction for us. So the light starts here, it goes along, hits the parabolic mirror and comes out, and they all come out in parallel lines. So the light's all in the direction that we're traveling. We get the same sort of thing happening with a satellite dish or a telescope mirror, but it's in reverse. This time what we've got happening is the information is coming in. It's being picked up by the dish. The dish then, parabolic, sends that information into the focus, and that's where we collect the information. So either the TV signal or the signals that we're getting from interstellar space, those sorts of things can all be then directed towards this focal point and collected and read. Zero gravity also comes into play with parabolas. If we think about weightless flight, so planes where they're trying to get some kind of zero-G thing going on, you might have seen these things where you've got people floating about inside planes. That only happens for a very short amount of time, for around about 20 seconds or so. And the plane has to follow a very parabolic path. And it follows that path and it gets its 20 seconds worth of weightlessness. And we get similar sorts of things happening on roller coasters as well. So roller coasters are designed with parabolic curves quite often, and those parabolic curves give us the feeling of zero G. So we have zero gravity effects on roller coasters as well. Right, bit of a recap on parabolas, what we've probably seen before. We've been looking at parabolas. So parabolas are what we get from quadratic expressions. And if we take the simplest form of a parabola, one that's centered at the origin, going to go through the origin, they tend to have this form. This is what we're used to seeing. Y equals some number times x squared. And if that number is positive, if in this case our a value, our constant, is positive, we get a U shape. We get an inverted U shape if a is negative. But to fit with the way we've been looking at ellipses and hyperbola, we'll be looking largely at parabolas which are horizontally aligned. So they're going to be this way round, where rather than our line of symmetry, our axis of symmetry being the y-axis, it'll be the x-axis. So that would just mean we'd swap. Rather than it being y is ax squared, we'd have y squared equals ax. Just swap the positions of the x and the y. And that would give us this. Where a is positive, that's what it's going to look like. Where a is negative, it would be over the other side. So if we have a horizontally aligned parabola centered at the origin, we can say the Cartesian equation is this. Now, notice what's happened here. We've introduced a 4, which wasn't there before. We just said previously it was a constant times x. Well, this is still a constant, the 4a, but the reason why we put a 4 in there as well will become apparent in a minute. Okay, so we tend to regard them as being in this form because it makes some of the other bits we're going to do in a minute just a little neater. We can also give a parametric form for this. So we looked at the parametric forms for the ellipse and the hyperbola, and they were involving trigonometric functions. The parametric form for a parabola doesn't involve trigonometric functions. It doesn't need to do that. And it might look a little odd when you first see it, but x is the same value here, the a times the t squared, and y is 2a times the t. T is allowed to be any real number, so positive, negative, fraction, decimal, rational, irrational, any real number, any number that we're aware of. And that's how you'd read that. T is an element of the real numbers. That's what that symbol there means. That's the set of real numbers. Let me just show you, though, why that parametric form works. So if I flip to my pen, let's start by looking at both sides of our Cartesian expression. So our Cartesian expression has on one side y squared. Well, let's have a look at what y squared is from the parametric form. So y is 2at, so y squared will be 2 squared, 4, the a squared, and the t squared. That's 2at all squared. 2at times 2at is 4a squared t squared. Well, that should be the same as 4ax for our parametric form to actually satisfy the Cartesian equation, the actual equation that we usually see for our parabola. So let's stick that in. Well, we're going to have 4a times, but x is at squared. So we can put in at squared there. So what have we got? We've got 4. This is an a, this badly formed a here. A times a gives us the a squared again, and t squared. And these two things then are the same. So it does mean that y squared was 4ax. Okay, the parametric form satisfies the Cartesian form. So this is the parametric form, a parametric form for our parabola. Okay. So just introducing some of the terminology we've been using again with ellipses and hyperbola. We've got a focus, and our focus will be at the point A0. We're just going to have a single focus for a parabola. Okay, ellipse and hyperbola, they've got 2 foci, and the directrix would be at the line x equals minus a. Okay, so the directrix would be at the line x equals minus a. Single directrix, single focus. Vertex is the origin, it goes through the origin, and we know our axis of symmetry is along the x-axis. Okay, that's the key stuff for us. All right, this is the reason really why we choose the 4a here in our Cartesian form. So we get the focus in a nice position, we get the directrix in a nice position. If I know the focus, I can jump straight into the Cartesian form. Yeah, if I know the directrix, I can jump nice and easily straight into the Cartesian form. Now, remember that the parabola is the locus of all points, such that the distance from any point to the focus is the same as the distance to the directrix. So we're saying the eccentricity, remember, is 1. All right, so if I take a general point here, the distance of that point to the directrix there has to be exactly the same as the distance to the focus here. If I trace around the curve and come to the vertex, you can see that that is true there. The distance to the directrix is a, and the distance to the focus is a. Okay, so it works there. The position of the directrix and the focus, they've got to be equal distances away from that point, the origin. So we'll end up with going through x is minus a, and we'll end up with the point there, a0. What happens if we move the vertex? So just as if we'd be moving the vertex or we're moving the center with circles, with ellipses, with hyperbole, what happens? Okay, if we go to the point P, comma Q, then the y is going to get replaced in our equation with y minus q, just as we'd have had with a circle. And our x is going to get replaced by the x minus p. Again, just like we've had with the circle, the ellipse, the hyperbola, all that kind of stuff. That's stepping away, that movement away. So if we're moving p along and q up, then we have to subtract the q from the y, and we have to subtract the p from the x. These brackets have been introduced here just to make sure that we remember that what we were doing previously, we were multiplying x, all of it, by 4a. So now we've got to multiply all of the thing that's taken the place of the x minus p, by 4a. All right, the focal length is just exactly the same here. So the distance from the vertex to the focus will still be a. So as a quick check on how you're getting on with understanding this. I'm going to ask you to pause the video in a second or two. But what I'd like you to do is to sketch these parabolas. So I'd like you to think about where is the axis, where is the focus, where is the directrix, and can you sketch the parabolas? What do these ones look like? Okay, so pause the video now. When you've had a go at all three, come back and we'll see how you got on. All right then, so let's have a look and see how we got on with these ones. If we start with y squared equals 12x, we know the standard form that we would like to see our parabola in is y squared equals 4ax. And when we see that form, y squared equals 4ax, we know that the a in there is giving us the position of the focus and also the position of the directrix. So I know for this one that my a value is obviously 3. So my focus will be at 3, 0, and my directrix will be at x is minus 3. Okay, so we should have vertex at the origin, focus 3, 0, directrix x is minus 3, and you should have something that looks a bit like that. If we move on to the next one, well, the next one, we've had a bit of a shifting going on. Things are happening to the y before we square it. Things are happening to the x before we add on, before we multiply the 12. But our a value is still the same. Yeah, the 4a in the front here, multiplying the x element, that is still a is 3. So we know our focal length is still 3. And we also know the distance from the vertex to the directrix is still going to be 3 as well. But where's our vertex? Well, we're subtracting 2 here. We're adding 1 here. So our vertex is going to move to the point minus 1, 2. All right. So that tells us where our vertex is. We know our focal length is 3. So we'll have to go 3 further along to get to our focus. So if we like, we can say that our focus then is 3 further along than that. It will be at 2, 2, and our directrix will be 3 further back from our vertex, just like we've got here. Look, 3 further back, 3 forward. So we can say that our directrix will be x is minus 4. Okay, so you should have something like that for this one. Yeah, vertex has moved. Our vertex has moved to here, the point minus 1, 2. Our focus is now at 2, 2, 3 along from that vertex, and our directrix is 3 back that way, so it's going to x is minus 4. Okay, our final one is quite similar to the first one. The first one, y squared equals 12x. Well, here we've got x squared is 12y. What's happened? The x and the y have changed places. So the orientation is going to change. Rather than this having an axis along the x-axis, an axis of symmetry along the x-axis, the axis of the parabola is now going to go along the y-axis, but everything else is going to stay the same. Okay, our focal distance is still 3, and our distance to our directrix is still 3 from the vertex. The vertex has not moved. It will stay at the origin, just swapping x and y around. 0, 0 goes to 0, 0. So what we had previously was this. So what you should have now, swapping the x and the y, is this. Okay, so our focal distance is 3. Our focus is now at 0, 3. Our directrix is now y equals minus 3. And our vertex is still at the same point that it was before. All right, we're now just going to have a quick look at the proof of the general equation of the parabola. All right, so if we have a parabola with a focus at a0 and directrix at x equals minus a, can I show that that means the equation of this parabola is y squared is 4ax? All right, we know that the distance here is the same, but how can I be sure that it's the same for every point along here? How can I show that this relationship must always be true? Y squared is 4ax. So let's start off. We're first of all going to think about a general point, P, and its corresponding point on the directrix to give us the shortest distance, x, and obviously that distance to the focus as well. So we need to think about what px is algebraically with our general point, x, y, and what PF is. Now, this point here, x comma y, well, that must mean I have to travel a distance of x before I hit the y-axis. Yeah, I've gone back. Its x coordinate was x, so I've had to go back x. I've traveled a distance of x till I hit the y-axis. The further distance I have to go to get to the point capital X then is another a, isn't it? Because that's what this distance is here. So this distance is a, this distance is x. The total distance then, from there to there, that horizontal distance, is just going to be x plus a. All right, the x from here, the a from here. All right, so that's px, that's quite easy. What about pf? Pf's a bit trickier. But what we've got going on in there is a right-angled triangle. Okay, so I'm going to try and draw this as well as I can. If I drop a vertical down there, nice vertical, I've got a right-angled triangle in there. And we know we can get the distance between 2 points by using Pythagoras. Yeah, this distance squared plus this distance squared must be the distance we want from P to F all squared. Okay, so just to recap that, this distance squared plus this distance squared is that. Okay, what is this horizontal distance? Well, the horizontal distance is the y-coordinate of our point, isn't it? It's starting at whatever the y-coordinate is and ending at 0. So that's my horizontal distance, y. That's quite easy. Vertical distance, apologies. Vertical distance is y. What's this distance here? Well, remember, this whole distance here is x. To take me to the point itself, where P is, that whole distance is x. This little bit here is a. So what's this bit? Well, it's obviously x minus a. All right, so if I think about building that then into my Pythagoras form, PF must be the square root of x minus a squared plus y squared. Okay, must be that way around because we've got to add up the squares of those two distances and then square root to get what PF is. Now, I don't like the fact this has got a square root in it, okay, and it makes it a little bit more difficult for us to just then go and say, well, PX and PF have to be the same because that's what the Focus-directrix property of a parabola says. I can put those two things the same, but the square root, I'm still not happy about the square root. How am I going to get to y squared equals 4ax? Well, if these two things are the same, okay, if these two things are the same, the px and the pf, then surely the square of these two things is the same. Yeah, if I square px, I must get the same as the square of pf. So that's the little trick I use to get rid of the square root. Square this, it must be equal to the square of this. All right, two numbers are the same, their squares are the same. So it allows me to say that x minus a squared plus y squared is x plus a squared. Now I'm going to need to multiply out my brackets. Okay, I need to do x minus a squared and x plus a squared. What's going to happen from there? Well, if I do that from the x minus a squared, x squared minus 2ax plus a squared. The y squared's already there. And on the other side, this expression, very similar to the one on the left-hand side, the only difference is the plus there. So rather than the minus here, we'll have a plus here. Otherwise, they're exactly the same. Okay, so we're going to get the x squared, a 2ax, and an a squared. Now, hopefully, you're a little bit ahead of me at this point, and you're spotting what I'm going to do next. We have got terms that are on both sides, so let's cancel them. The x squared appears there, and it appears there. Let's get rid of them from both sides. Take it away. The a squared is on both sides, so take them away from both sides. And we're now left with something that reads a little bit easier, aren't we? We're now left with something that's actually quite close to where we want to go. Minus 2ax plus y squared is 2ax. If I add 2ax onto both sides, I'll get left with y squared and 4ax. And we're done. So we've started with the Focus-directrix property, and we've managed to get to our form for the general equation of a parabola. All right, some more questions for you to think about. All right, 5 minutes, I think. Pause the video, have a little bit of a look at these. For the first couple, we're trying to get the equation of the parabola. Okay, we're told where the focus is and where the directrix is. For the third question, you're told the equation of the parabola. Can you get where the focus and the directrix would be? And if you think you want to have a go at a few more, there's a couple of questions, an extension at the bottom that you can have a think about. See if you can do those ones too. All right, so pause the video. Come back when you've had a look at those. All right, so let's have a look at how we've got on with these ones. So the equation of the parabola with focus 7, 0 and directrix x is minus 7. Well, that's telling us a straight away is 7, isn't it? Remember, x plus 7 equals 0 is x is minus 7. All right, it's just a little bit disguised, isn't it? All right, so x is minus 7. So we've got our a value. Our a value is 7. So we're just going to get y squared equals 4ax. Y squared is 28x. Similarly, on the second one, our focus gives us the a value. Our a value is root 3 over 4. If we do 4a times x, that gives us y squared. 4 lots of root 3 over 4 gives us root 3. So we end up with y squared is root 3x. The coordinates for focus and equation for the directrix of each one of these underneath. Well, here we've got on that first one that 24 is 4a. So a is 6. The focus must be at 6, 0. And the directrix must be x is minus 6. For part B, we've got root 32 is 4x. Okay, so, sorry, is 4a. Root 32 then, if I write that down, is 4a. If you're thinking about how you deal with square roots, 32 is 16 times 2. 16 can come out, leaving us with a 4 when it's had the square root done to it. 4 root 2 is 4a. Okay, a is root 2 then, isn't it? All right, that will go. That will go. A is root 2, so the focus is going to be at root 2, 0, and the directrix is going to be x is minus 2, root 2. If you did the extension questions, just flip those ones up quickly so you can have a look, see how you got on with those ones. All right, hopefully not too badly. Just remember on that fourth one there, because we've got x squared is 12y, the focus will now be on the y-axis, not the x-axis, and the directrix will be in terms of y as well. All right. Now we're going to look at something that has a little bit of an unusual name, the Latus rectum. So the Latus rectum of a conic section is a line segment, okay, a line segment drawn through the focus, which goes perpendicular to the major axis or axis of symmetry, and it has its ends on the conic section itself. All right, the words not so easy to understand without a diagram. So we'll come to that in 1 second. But it goes through the focus, it's perpendicular to the major axis, and its ends are on the conic section itself. For a parabola, the length of the Latus rectum is really easy to find if we know the equation of the parabola. So here's my sketch. Okay, here's my diagram. So I'll flip back to my laser pointer. This is the Latus rectum. Okay, it goes through the focus, it's perpendicular to the axis of the parabola, and its ends are on the parabola itself. Okay, that is the Latus rectum. Well, we can find this length from A to B actually quite easily. All right, so let's have a look at how we might do that. Now, at A and B, we know the x-coordinate is A. Yeah, both cases the x-coordinate is A because it's directly above the focus or directly below the focus. So we can now substitute that into y squared equals 4ax. We can hopefully work out what the y-coordinate is. So y squared is 4a times a, which is 4a squared. All right, well, let's just square root then to get what y is. We have to remember we're going to get a plus or minus when we do a square root. So y squared is plus or minus 2a. Okay, so y is plus or minus 2a. So at a, we have the coordinates a and 2a, the positive y value. And at b, we'd have coordinates a and minus 2a. Well, what's the distance now between a and b? This y-coordinate is 2a. This y-coordinate is minus 2a. Nice straight line up and down. Hopefully you can see the distance is just 4a. To go from here to here is 2a. To go from here to here is 2a. So the length of the latus rectum is 4a. This is what features in our equation. If we say y squared equals 4ax, we're actually giving the latus rectum length for our parabola. All right, why latus rectum though? It's an odd term, isn't it? It's a compound of two Latin words. So you've got latus, which is side, and rectum, which means straight. The straight side of a conic? Well, maybe it's straight. Does conics have sides? Going back even further, it used to be called the latus erectum, which might make a bit more sense because it's perpendicular, isn't it? But that's the term that we use. Why are we interested in it? Why is it important to us? Well, latus rectum and eccentricity are really important together when we describe the motion of bodies in astronomy. It's just a little bit of a side for us really here to look at the latus rectum and see how it relates to the parabola. The semi-latus rectum is half the length of the latus rectum, and it is the radius of curvature of the planet's motion at perigee. That's the fastest point near the sun. So let me just, if I think about, if I do a little sketch, maybe this is going to help a little bit. So if I think about an elliptical orbit, okay, a planet's elliptical orbit about focus there. So there could be our sun, and there's the planet going around the sun. Okay, the path it's going to make. So the radius of curvature at the point right at the closest point, the fastest point near the sun, this point here, where the planet's going fastest near the sun, okay, the radius of curvature, how curved that ellipse is actually given by the value of the semi-latus rectum. What else? Well, if we think about the extreme positions of the planet from the sun, so we've got this position here, the closest position, and then we've got the position that's furthest away. Right, if I put in my coordinate system and make that the origin, okay, this distance from here to here is the focal distance. Yeah, so we could call that C. That distance there is C, just there to there. This distance on the other side here is A, because of the way we express an ellipse. So this distance in here, the distance from the sun here, must be A minus C. So A minus C is the closest distance. This distance just in here. The closest distance the planet has to the sun is A minus C. And the furthest distance it is from the sun, well, it has to go from there to there. So that's A plus C. All right, so the extreme positions are A plus C, A minus C. Now the semi-major axis of the ellipse is the arithmetic mean of these two positions, the usual mean that we talk about. If I add these two things together, the C's cancel, don't they? Because I've got a plus C and a minus C. I get 2A. 2A. If I halve it to get the mean, I get A. Well, that's the semi-major axis. So the semi-major axis is the arithmetic mean of these positions. The semi-minor axis is the geometric mean. Geometric mean is something you don't tend to think about an awful lot when you're just looking at averages, but there are other forms of the mean. The geometric mean, just if you're interested, it involves multiplying the two things together. Or if you had more than two things, it multiplying 3, 4, 5 things together. And then taking the corresponding root. So rather than halving it, like we would do when we've added them, we take the corresponding root. So we do the square root of all of that. Now, this is A squared minus C squared. If I multiply it out, but A squared minus C squared for an ellipse is B squared. So the geometric mean gives me the length of the semi-minor axis. Okay. And then the semi-latus rectum makes this up. So we've got the semi-major axis, semi-minor axis, semi-latus rectum, the harmonic mean. What's the harmonic mean? To get the harmonic mean of two numbers, what you do is you get the reciprocals of each number first, and work out the arithmetic mean of those reciprocals. Then take the reciprocal of that answer, and you've got the harmonic mean. If you wanted to have a look, see if you can prove that the semi-latus rectum is the harmonic mean. If you do the reciprocals of each one of those, A plus C and A minus C, take the average of those reciprocals, and then take the reciprocal of that. Do you get 2a, the semi-latus rectum? Yeah. So the latus rectum length is 4a, isn't it? Do you get 2a? Well, actually, you do. So that's quite nice. Arithmetic mean is a semi-major axis. The geometric mean is a semi-minor axis, and the semi-latus rectum is the harmonic mean. Don't need to know any of that. That was just a little bit of an aside if you were interested. All right, so at the end of our lesson, we've got y squared is 4ax is the standard equation of our parabola. The vertex in this case will be the origin. The focus will be at the point A0. The directrix will be at the point the line x equals minus a. The length of the latus rectum is 4a. This line here is 4a. Okay, if we look at it on this diagram, we can see that's 6, and that's 6. It's 12, isn't it, for that one? And that is exactly 4 times a. All right, a there is 3. And if the parabola's got a vertex at PQ, we just shift the equation along so it looks like this. Okay, the Q has to be subtracted from the Y, the P has to be subtracted from the X, and then we've still got the same form of the equation, just as we did with the ellipse, the hyperbola, the circle. So that's it for today. Well done.